Hi everyone, and welcome to lesson 4, graphing the quadratic function. So after lesson 3, when we learned to graph from factored form, which is this form right here, the way we did that is we looked at x-intercepts, which we found using the zero product property. We found the midpoint of that, and from there we were able to calculate our vertex x and y values, and we were able to graph a factored quadratic using 3 points. We also talked briefly about this form, standard form, when we talked about patterns and finite differences in a previous lesson. So the focus of today's lesson is, as you can imagine, our middle version here. Of course, these all represent quadratics, but this is the one we're looking at today, vertex form. So before we get into graphing, the first thing I wanted to do is cover something I think you've seen before, but it's just translating very simple geometric figures when they're presented to you in a grid. So there's a way to do this in a very simple form, basically just by counting squares. So if we're to take this triangle example, WEG, and we want to translate it 3 units right and 5 units down, it's as simple as it sounds. We basically look at E, we look at the point, we move it 3 across, we move it 5 units down, and we're going to denote it as E prime, which is conventional to just put a little tick beside your translated point. We're going to do the same thing here, G prime, and the same thing here, 2, 3, 4, 5, W prime. Of course, you don't need to actually include these things in there. It actually looks pretty ugly. Oops. 1, 2, 3, 2, 3, 4, 5. And if I've done this correctly, it should have the exact same shape and the exact same orientation. It's just translated or slid along the plane. Now, if we look at this wave example here, what we can see is that the points aren't super easy to see, but there are some that are a bit easier to nail down than others. Okay, so we can see that sort of at the halves and at the holes there are points, and I'll just use a different color. Basically what we want to do is translate 1 unit left and 3 units down. So maybe let's look at these 2 points at the moment. So we want this to move 1 unit across, so this way, and 3 units down. 1, 2, 3. We're going to do the same thing for this half. 1, 2, 3. And here, and here, and here. And although you don't know this yet, or maybe you do, this is called something we call a periodic function, meaning that it's cyclic, and it'll just keep repeating this over and over again. And for those of you who have seen trig, who know it, know that this is actually a sinusoidal function. And I thought it might be a good idea to show you that it's just as easy to translate a sinusoidal function as it is to translate a parabola, as long as you do this thing called point mapping. All right, so we've got the idea. Okay. All right, I want to do 2 more examples before we move on. So with this figure, I've given you points here. So I've also given you a graph, so we might as well graph it. So we've got -4, -3. That's R, -4, 0. Okay, so now what happens when we don't have a graph? can we still translate these units? Well, yes, we can. We're just not really going to see what they look like on a graph. But the whole system of coordinate points means that we're actually able to map them even if we can't graph them. So as you can imagine, if we had a grid, what we would be doing is, in order to move these 15 units to the left, what we would be doing is actually subtracting 15 from all the x values in order to move them left. So let's do that. And if we were to move it 25 units down, we would also be subtracting 25 from the y values. All right, so we have our new translated points. All right. So that's just a really quick intro to what the method I want you to use to graph quadratics once we get there. Now, before we actually are able to transform a quadratic, we first need to know what the most basic one looks like. So that's what we're going to do right here. So right now we're looking at a quadratic function. They all take this general form, and we're going to call it vertex form for a reason that becomes pretty clear in a minute. So what happens when I take this form, but I take the most basic version of it, and that is what happens if I let a equal 1, h equals 0, and k equals 0? Well, we get this function. And this function, y equals x squared, is what we call the parent function, which I'm going to spell like this, to all quadratics. Okay, so it's the basic function that we're going to start moving and changing in order to make other functions. So the way I graph it is really simple. I'm just going to use a table of values. And typically what you want to do is take a few values before 0, 0, and a few values after 0 for any parent function. Okay, so when I square -3, I get 9, 4, 1, 0, 1, 4, 9. And then I'm going to plot it here. Okay, and then we're going to join it. And make sure, as I said before, I like it when you actually fill in the field of view of the graph. Okay, so we have an idea, and what's good to know is that the shape of this is always the same. A shape of a parabola will either take this shape of a U or an upside down U. And another thing we want to notice is that there's a line here in the middle whereby if I were to fold this thing over onto itself, it would fit exactly. So the shape is that of a U. It's also symmetric. Okay, and what we'll also notice here is that it has a minimum value. Okay, and if it were happened to be oriented like this, it would have a maximum value. So these together are what we call a turning point. So either a maximum or a minimum is what we call a turning point. Okay, and another word for a turning point is a vertex. Okay, so that's why we call this, well, you'll see in a minute why we call this vertex form. But first, what I want to do is pause and move us into GeoGebra so I can show you a nicer view of this graph that's not drawn by hand by me. So here I've actually input my, don't worry about the f of x, we can just assume that is y. I've put in my quadratic, And using these, what we call sliders, I've currently set my A value to 1, my H value to 0, and my K value to 0 as well. So I'm going to graph this, and obviously it looks nicer than my pen on my iPad. I don't expect you to be perfect, but I do expect you to hit those important points, okay? So right here we have -3, 9. We have -2, 4. We have -1, 1, etc. Okay, so it should generally go through those important points. So that's one thing. The second thing I wanted to do was just point out some really important things about this graph. There are names for some of these things, and first of all, the name of the graph of this is called a parabola, and we'll notice that there's a very distinctive point right here at the bottom. So in this case, this parabola has what we call a minimum, and actually the minimum value is more generally called a vertex. So a vertex is where the parabola either reaches its lowest point or where it reaches its highest point. Because sometimes, and as we'll see next time, these can be reflected, they can flip around. So a parabola either has a maximum or a minimum. Those are called vertices, or singularly it's called a vertex. Now, while I have you on GeoGebra, what I wanted to show you is that for today we're not going to worry about A, but I want to show you what happens when we actually have an H and K value. So let's start with K because I think it's a little bit easier to see. So if I actually use my slider to move K and give it a value other than 0, we can see that actually my equation goes from x squared to x squared, in this case, plus 2.3. And what we can see actually is when we slide through the values of K, my parabola maintains exactly the same shape, but it's just moving up and down. So what we can see is when K changes, our shape translates, just like we did at the start of our lesson, it translates vertically by however many units K says. If K is positive, it goes up. If K is negative, it goes down. So let's stop K at, I don't know, we can stop K at maybe, actually let's go back to 0. Okay, because the next thing I want to show you is what H does, and as you can imagine, H does the same thing. Okay, it just moves left and right. And I just want to point out something you really, really need to be aware of because it causes a lot of confusion, and that is this negative sign. Okay, so what we'll notice is when H is positive in terms of its value, let's wait till it goes positive again, or maybe I'll do this. When H is positive in this value, meaning it goes to the right, okay, in your equation it shows up as negative. Okay, and what I mean by that is H itself is positive, but by definition and by convention, this sign is always negative. So when I see x minus H here, or x minus 2.6, the H value is actually 2.6. Okay, it's not negative 2.6. So something really, really important to keep in mind.